in all of its forms in the universe, everything from microbes on Mars to extraterrestrial civilizations. If you want to find out more about us, please do go to our website, SETI.org, and I will stop there and let Franck Marchis, our Senior Planetary Astronomer, take it away. So over to you, Jessica.
Thank you, Simon, and thank you to the SETI Institute. We've really enjoyed this partnership, and it's so wonderful to hear from the experts that you have on your team. And now I'd love to introduce you all to Dr. Franck Marchis. Dr. Marchis is a Senior Planetary Astronomer at the SETI Institute and Chief Scientific Officer at Unistellar. Passionate about astronomy, he has dedicated most of his research to the development of adaptive optics on large telescopes to study asteroids and search for exoplanets. Unistellar is a private company whose goal is to create the largest network of citizen astronomers around the world, capable of reconnecting with the dark sky with a digital smart telescope and collecting scientific data for space agencies. And we will also take questions from the audience at the end of Dr. Marchis's talk, so be sure to post your questions in the chat. Thank you, Dr. Marchis, for joining us.
Thank you. Thank you very much. Can you hear me well?
Yes, sounds great.
All right, great. Okay, so this is a talk kind of that I put together a few days ago because I wanted to talk about exoplanets and specifically. So let's just mention, first of all, that when I say the word planets, I generally talk about planets in our solar system. So I'm talking about the 4 terrestrial planets, Mercury, Venus, Earth, Mars, or the 4 gas giants or ice giants like Jupiter, Saturn, Uranus, and Neptune. When I talk about exoplanets, I meant extrasolar planets. So I meant here planets which are in orbit around other stars. And I'm going to try to be careful not to mix up these two words so you know why I'm talking about here. So first of all, I should mention that I work at the SETI Institute. And as part of the SETI Institute research, I'm a researcher dedicated to answering to these very simple questions, which is basically the question that most of us ask when they look at a star, and there's so many stars in the sky. So if you look with a naked eye, you will see, if you can count them, roughly 3,000, 4,000 stars, and they're very good sky, very good condition. If you're in city, you will see maybe a handful of them, unfortunately. When you look at the sky and you see all those stars, you probably wonder if around those stars there is planets. But in fact, we learned a lot about astronomy recently, about the galaxy, and we have an answer to that. And one of the key part of my talk is to describe to you what we have learned about the presence of exoplanets in orbit around stars in our galaxy. And this will help us to understand whether or not we are alone, of course. So first of all, let's talk a bit about the Milky Way. So the Milky Way is our galaxy. That's the name of our galaxy. It's a medium-sized galaxy, part of what we call the Virgo cluster. There is like 3 trillion or 20 trillion galaxies in the universe. So there is more galaxies in the universe than there is trees on Earth. So there is a lot of galaxies. And galaxies have different age, of course, depending on where they're located. But let me just say that our galaxy is roughly 20 billion years old, just to simplify. We are located in one of the arms of the galaxy. So in the center of our galaxy, we have a black hole and star orbit around it. And we're located in one of these arms, in the Orion arm, 1/3 away from the center. When I say we, I'm talking about our solar system. So our solar system is, as I mentioned previously, is made mostly of a star, the sun, which is a gigantic star which contains 99% of the mass of the solar system. And around these stars, we have tiny confettis, and those are planets. The largest one is Jupiter, but then the terrestrial planet, especially our planet, is very small compared to the sun. However, our planet is very special. If you look at our planet, if we compare an image of our planet with any other terrestrial planets around it, like Venus, Mercury, and Mars, you will see that we have a very colorful planet, a beautiful planet. We live on a planet which is mostly blue and with clouds because of the presence of liquid water. This basically is a game changer because no other planets have oceans like ours. Because of the ocean, we believe that life appeared very quickly on Earth. Earth formed 4.5 billion years ago, roughly. Life, the first presence of life, appeared 3.8 billion years ago. So very, very quickly after the formation of our planet. And this life thrived on the surface of the planet, diversified 800 million years ago, become multicellulars with a more diverse biosphere, and then came what we call the intelligent life, ourselves, which appeared to be 2 million years ago. So our planet is unique and very different because of the presence of liquid water and then life. And one key part of the research of an astronomer at the moment, especially astronomer like myself, who study and search for exoplanets, is to find one day a planet like Earth somewhere in our galaxy. An Earth 2.0, a cousin of Earth, you name the way you want it, but we want to find something that looks like our planet. So if you look at the sky, as a human being, what you see, it's mostly stars, tiny dots that occur due to the presence of the atmosphere of our planet. These stars are not in fact stars. What we discover, and this will be possible to see if we had the better vision, if we were able to see like Superman here, if we were able to see with better, more accurately, see better details, we will see that in fact, the universe, the galaxy is not full of stars, it's full of planetary systems. Stars with tiny planets or big planets around them. So this is what you will see if you were Superman. This is the kind of view you will have. Around each of these tiny dots, you will be able to see those tiny planets and get information about those planets. So how did we find this, since we are not Superman? Well, we found that because we launched space telescopes, and especially one of them called Kepler. Kepler was launched in 2009, and Kepler basically was a telescope of a relatively small size, roughly 1.2, 1.5 meters, that stared continuously one area of the sky, close to the Cygnus constellation. And he had a very large field of view. And what Kepler did is to look continuously at those stars to see if some stars had their brightness, which drop based on the fact the planet in orbit around the star was passing between us and the star. That's what we call a transit. It's basically a small occultation, a small eclipse of a star, of a planet passing between us and the host star. This is what you can see here, for instance. And because of this measurement, Kepler observed 110,000 stars for 4 years. And because of that, we now know that around each star in our galaxy, there is 2 planets. And that's a game changer. Because before, we really thought that planets were rare. Now we know that planets are everywhere. And when I say they're everywhere, I meant there is like 250 million stars in our galaxy. So there is roughly 500, 600 million planets in our galaxy. And that's a very big number. So we cannot, of course, we don't know yet all the planets in our galaxy. Thanks to Kepler, we discover like roughly 3,000 exoplanets, and other missions, other telescopes on the ground in space discover 1,000 other exoplanets. And this diagram show, I think this was done when there was roughly 1,500 exoplanets at the time. And that's a diagram showing the exoplanets we know so far. And of course, I'm not going to spend my entire time talking about each of those exoplanets individually, because it would be very boring, and we'll be spending the entire night here talking about each of them. And additionally, they don't have names. We're going to talk about that later on. They have code names, so they're really not that interesting if you look at them individually. But we discover some remarkable things by observing those exoplanets, by detecting them. And that's what I want to show you briefly now. So this diagram is a bit complicated, but what I really want you to understand here is that what astronomers often do is that when they observe something, and there is numerous of them, like asteroids, supernovae, galaxies, and now exoplanets, they classify them. That's what we love doing as astronomers. We put planets or those bodies into categories, and then we start dividing ourselves, so the work is easier. Some astronomers we start observing hot Jupiter and understanding how we form hot Jupiters. Other will basically focus on terrestrial planets. So we split the research into those subcategories to make it easier for us to communicate, and also because they give us, statistically speaking, some information about how they form, where they come from, and how they evolve. So this diagram, what is very important here is to understand that the yellow, the kind of ellipses here show basically categories. So there is planets like Jupiter, planets like hot Jupiters, other planets called ocean worlds, rocky planets, lava worlds, etc. And that's what I'm going to talk about now. I'm going to give you a few examples of some of them. So let's talk about the first and the easy one, the cold gas giants. So our solar system has two cold gas giants, Jupiter and Saturn, that you see here. So Jupiter and Saturn are, as I say, gigantic. You can put 1,000 Earth into a Jupiter. So that's a very big planet. It's a planet made mostly of gas, mostly hydrogen and helium. If you look at the planet, Jupiter and Saturn, you will see them, they're roughly the same color. They're orange, yellowish. This is due to the presence of gas on the upper part of the atmosphere. But most of the rest of the planet is really homogeneous, made of hydrogen. So we call them cold gas giant because they're gigantic, because they're made of gas, and because they're cold. When I say cold, we are talking about temperature, which is temperature roughly minus 200 degrees Celsius. So very, very cold worlds. In this type of environment, the chemistry is very different, of course, compared to what we have on Earth. So we have discovered more than 50 cold gas giant planets. They're interesting because they tell us about the way this planetary system form and how they evolve. But now let's focus on something which is very exotic that we don't have in our solar system, called hot Jupiters. So the first exoplanet we discovered in 1995, called 51 Peg b, was in fact an exoplanet which was orbiting around the star in a few days and very close to the star. That's what we call them, hot Jupiters. So we don't have picture of hot Jupiter exoplanets. We only know they exist because we detect them by direct method, such as the transit I mentioned to you, or other method called radial velocity. There is questions about that. I can discuss this later on. But what we know is that they exist, they're there, and they must be very impressive systems, because you have a gigantic Jupiter-sized exoplanet, and sometimes even bigger in mass, orbiting very active stars. So of course, there is an interaction between those two worlds, because the planet is very, very close to the star. So what we have seen by observing those hot Jupiter, we detect them, but sometimes we also detect that they are more like comets. They're losing the gas because of the solar wind, the very powerful wind coming on the planet and blowing away the atmosphere. So those planets will not stay there forever. After probably 100 million years, they will become drier and lose their atmosphere. And I'm going to go back to that later on. So this is an artistic view of one of them. And as I mentioned to you, most exoplanets have a code name. They don't have a real name because we're kind of lazy, and we decided to name only 100 of those exoplanets so far. So another kind of world is what we call ocean worlds of ice giants. So they're very weird as well. Let me talk first about the one we know, the ice giants. So those are Neptune, Uranus, exoplanets. They are like those gas planets that we have in our own solar system. They're made mostly of gas. As I say, they're medium size, 10 times the mass of Earth, and they're far away from the star. We have seen those ice giants we have detected those ice giants around other stars. So when we detect a planet like similar to our own planet, we can of course make some comparisons, some assumption about the composition, the mass, the size, and the way these planets come from. But in the case of the second, sorry, I want to mention that we can also understand better the internal structure of those exoplanets. So we have sent spacecraft around Jupiter and Saturn, which orbit around the planet for years. Galileo spacecraft, and recently we have Juno in orbit around Jupiter. And those spacecraft orbit around the planet and sometimes around the satellites as well, and give us information about the planet itself. Pretty pictures. True, we can see the surface of the planet. Direct measurements, we can hear the planet, hear the radiation coming from the planet. But we can also very accurately measure the orbit of the planet. And by measuring the orbit, we are capable of knowing the internal structure of the planet. And what I meant by internal structure is basically what the planet is made of. And that's one of the most interesting reasons we're sending spacecraft over there. It's not only to get pretty picture, but really to understand the internal structure of those planets. So Jupiter and Saturn are more or less the same because they are giant planets. They're made mostly, as I mentioned, of hydrogen. But something that is very interesting is that they're so big that the pressure is super high in the center. So the hydrogen becomes something that we don't have on our own planet. It becomes metallic hydrogen. And this metallic hydrogen does not exist on our planet. And we're trying to create it, in fact, not too far away from San Francisco at Livermore. There is a lab which is basically trying to produce this very high pressure environment to see how the hydrogen will become and what structure it will take. So we have mimic the interior of gas giants in labs. Uranus and Neptune are different because they're smaller and they don't have the same composition because they don't have the same pressure as well. We suspect that they have a mantle, which is kind of liquid or slushy icy. Like it's basically a slush, this famous slushy that you drink when you go to a theater, made of ice mixed with some kind of material, which are generally red or blue that you drink. But they're made of more or less the same kind of material, we believe. Very porous, very cold, and made of small crystalline features. So something interesting happened is that when we observe those exoplanets, we also detect things which are unexpected. And sometimes we detect dead bodies around bodies which are alive. So this is one of them. This is a result that came out very recently. I think it was like less than 4 months ago. It's a detection of what we call of a Jupiter-sized exoplanet, so a gigantic planet, in orbit around a white dwarf. So the white dwarf is basically the heart of a sun. When the sun ends his life, he's basically going to eject his upper atmosphere, forming what we call a planetary nebula. And at the middle, we find the skeleton of the sun, which is a core. And what you have here is a Jupiter-sized exoplanet that somehow survived this explosion and come very close to the skeleton, the bone of the star, the white dwarf, and is now in orbit around this white dwarf. So this system is new, and it's something we did not expect to see. And we discovered that thanks to a mission, which is called TESS, the successor of the Kepler mission. The planet orbit very close to the white dwarf in 1.4 days. So that's the year is very fast over there. And then we have also the contrary. And in this case, what we discover again with tests, it's a new planet called TOI 849b. As I mentioned, they don't have names, they have code names. So this is a code name. And this is a gigantic planet the size of Uranus and Neptune, but terrestrial. So made of material which is terrestrial, so basically made of dense material like rocks. And that's something unexpected, because there is one thing we did not expect to see, is to find planets that could be as big as Uranus and Neptune, but made of solid material. And we think that what we are seeing here is not a planet. It's basically the core of a gas giant that get vaporized because it comes very close to its star. And you remember I showed a picture previously of a planet comet that was losing its gas. So what you can see here, it's basically the core of a Jupiter-sized exoplanet after losing all its atmosphere. So this is a dying planet of, I would maybe say, a planet which is dead in this case, very close to its star. And then we have weird planets that don't exist in our own solar system, but theoretically should exist, we believe. And those are ocean worlds. So those ocean worlds should be planets the size of Uranus and Neptune, but covered with a gigantic ocean. Theoretically, they exist. We have seen worlds that could be those, but we have not taken a picture of them. So we don't really know much about them except the size and their orbit. And those are very interesting because that's something that we don't have in our own solar system. So we're gonna learn a lot about those exoplanets, and we're gonna probably learn a lot about how they form and how they evolve in the future. So let me go back to something like we know now, terrestrial planets. So remember, terrestrial planets are made of rocks. So Jupiter, so Mercury, Venus, Mars, and Earth are basically rocky planets. I would like to talk about one specific system. It's called TRAPPIST-1. That was announced in 2017, 2018, I think. So this is a system of planets. It's made of 7 planets that we call TRAPPIST-1b, or TRAPPIST-1c, TRAPPIST-1d, etc. You got the idea, right? This system is interesting because the planetary system here is not in orbit around a gigantic star like our sun. It's in orbit around a tiny, called M-dwarf stars, the size of Jupiter roughly. It's a very small star, which is not super hot, but live for a very long period of time. And those planets are very close to the star. So I want to discuss about that, because one of the things which is very important for us is the location of a star and the temperature of the location of the planet and the temperature of the star. If a planet is too close to its star, it's too hot. So it becomes basically, if it's terrestrial, it will lose its atmosphere, and it will quickly become too hot to have liquid water. If a planet is too far away from its star, it becomes too cold. That's, for instance, Mars is a cold planet for us. We cannot live on Mars. A planet which is too hot is Venus. We cannot live on Venus because at the surface, the temperature is 300 degrees Celsius. But if you're just in between, like Earth, you will have a temperature which is appropriate for liquid water on the surface. So this system has interested a lot of astronomers because it's made of 7 planets, and 3 of them are located in what we call the habitable zone of the star. So that's what is shown here in green. It's an area where basically, if you have the same kind of atmosphere than our planet, you could have liquid water. And that's important because you remember I mentioned previously that if you want to have life, we think we need to have water. So those planets could have liquid water. We never say there is life on them, but the fact that they could have liquid water is indicative that they could be habitable. That's why we call them potentially habitable exoplanets. So artists has made diagrams, figures, drawing about those exoworlds. And this is TRAPPIST 1e, seen the surface of TRAPPIST 1e. So you can see the M dwarf, which is very faint and reddish, small sun, but it's extreme. The planet is very close to the sun. It's like 1% the distance between us and our sun. And you can see some other exoplanets located even closer to the star. And at the surface, because the planet is in what we call the habitable zone, you could have liquid water, like you can see here. But watch out, what I mentioned here, I always say detected. I don't say that we have seen water. We have never detected water. And I'm gonna go back to that later on. So let's talk about something very exotic once again. Those rocky planets, they could be as well very close to the star. And in this case, the temperature of the star is so, the temperature on the surface of the planet is so high that it can reach the temperature greater than the temperature of the rock. So the rock become liquid. And the entire planet become a gigantic lava world. So we have seen those planets, we have detecting those planets. They have not been seen yet, but we know that Kepler planet like Corot 7b, Kepler 10b, and Kepler 78b, I told you they have very bad names, are in fact possibly lava planets covered with lava on the surface because of the temperature. So we have not seen them, but science fiction love them. I think if you watch science fiction movies like Star Trek, in Star Trek there is a lava world planet called Mustafar. There is an epic battle on Mustafar in one of the Star Wars. Sorry, and of course we have picture from artists to illustrate what it will be to live on one of those extreme worlds. Okay, so I want to finish by talking about what scientists want to do now and in the future. What's the main goal? What we call the frontier in science. But one important part is that everything I show you before are artistic views. None of those are pictures of an exoplanet. Because we don't take pictures, we see the planet indirectly. And we don't see the planet, we see the shadow of the planet, like this. And this is possible because the planet is passing between us and the star. So when you see the shadow, you have a rough idea of the size because you know the size of the star, and you know the size of the shadow, so you can estimate roughly the size of the planet. But that's all. And the orbit. We don't know if the planet is like Earth, if it's like Venus, or if it's like the moon. We have no information. However, and that's what the slide is showing here, we have a lot of planets which are the same size roughly of Earth and located in what we call the habitable zone. So this is the name of some of them. As again, some code names, I'm sorry for that. And their distance to us. The galaxy is 100,000 light years. And here we're talking about worlds which are 4 light years away from us. So they're very close to us. They're in our neighborhood, basically. So those potential worlds, those worlds could be habitable, like the TRAPPIST that you can see here. But those pictures here are not pictures of the planet. Those are artistic views made by an artist to kind of try to imagine what the planet will look like if it had liquid water on the surface. So what we want to do, the new generation and the new generation scientists coming after me, of course, is to image an exoplanet, to see an exoplanet, and to see specifically a planet like Earth. But that's a gigantic challenge because a planet like Earth is super small. Earth is tiny, I mentioned that previously, compared to Jupiter, and Earth will be even tinier compared to the Sun. So if you want to see an Earth-like exoplanet around a gigantic planet, star like the Sun, you will have to have a very good instrument, something that can detect a very faint object nearby a very bright one. We often say that it's like trying to see a firefly in orbit or flying nearby a lighthouse at 400 kilometers. That's a gigantic challenge. And that's a bit of the challenge that we are trying to do as astronomers. But it's a gigantic challenge, but it will be a remarkable discovery. Because if one day we find a planet like Earth, and we take a picture of it, from the picture we know the color, and from the color we know there is an ocean, there is continents, there is gas on the surface with clouds, seasonal effect, etc. And that's really the true motivation of the research I'm doing at the moment. So how can we do this? Well, there is various ways. So first of all, the best way is to go to space, because space is a good environment, it's stable. And when you send a big telescope like the Hubble Space Telescope, you take full advantage of the environment. Unfortunately, to observe something like an Earth-like exoplanet, a planet like Earth, you need to have a much bigger telescope. So NASA has been developing ideas, concepts based on this objective, and this is one of them. Is called the LUVOIR telescope. The LUVOIR telescope that could fly maybe in 2040 will be capable of observing and detecting planets like Earth and characterizing them. And what I meant by that is that to see the planet, take a spectrum, see the color, know the composition, know the temperature on the surface, etc. And this instrument could detect up to 300 Earth-like exoplanets. That's a big motivation. And fortunately, projects like this are not easy to do. They're extremely expensive. We're talking about $20 billion to build something like that, even more. And we don't really know how to build 8-meter, 11-meter telescope in space yet. We have not done that yet. So there is other projects, and I'm not going to go through all of them, but some are called ABEX, like the one you see here, which has this kind of petal-like coronagraph that can help to get a better image of the planet. We have WFIRST here that will be probably doing some kind of experiment to show that we can image exoplanet from space. Those instruments will all be equipped with this system that improves the quality of the image, called adaptive optics. So another way, and that's something that I want to mention now to finish with, is to build an instrument which is not going to observe all the stars, all the bright stars, but focus on a few of them. And one of the systems which interests us the most is the system called Alpha Centauri. Alpha Centauri is made of two sun-like stars, Alpha Centauri A and Alpha Centauri B, that you can see here. And in orbit around those two sun-like stars, what we call an M dwarf that I mentioned previously, called Proxima Centauri. We have seen and detected terrestrial exoplanets around Proxima Centauri that we call Proxima Centauri B and Proxima Centauri C. So now the goal of astronomers like myself is to develop instruments that will be one day able to image an Earth-like exoplanet around those Alpha Centauri A and B. So and to do that, we had a crazy idea. And the crazy idea is this telescope. So this is the European Extremely Large Telescope. It's going to be a 45-meter telescope. That's the size of the aperture, 45 meters. It'll be taller than the Eiffel Tower. or the Statue of Liberty. Inside, you have a gigantic mirror made of 100 small hexagonal segments that will be together on this gigantic mount here. And this telescope will be able to steer and follow very accurately a star in the sky. And because we really like science fiction, it's not only what we're gonna do, we're gonna also, because we want to have the best image quality possible, we're gonna create with this telescope a fake star in the sky that will be used as a reference. That's what we call a laser guide star. So this telescope is actually in construction in Chile, in the southern hemisphere. There's another one that's also being built by university in the United States called the GMT, the Giant Magellan Telescope. And there is another one that's gonna be built in Hawaii called the 30-meter telescope. And those telescopes are made to observe galaxies, nebulae, etc., but also to be able to detect and to characterize one day an Earth-like exoplanet. And that's what I was mentioning to you, the Star Trek-like laser guide star. So what exactly concretely we will see is this. So this is a telescope, 45-meter aperture. The TMT will be able to do the same. And we are thinking about designing an instrument that we call Tiki, it's a code name at the moment, that will be a ball, and that's a simulation of observing Alpha Centauri A and detect in orbit around Alpha Centauri A Jupiter-sized exoplanet, but also an Earth-like exoplanet. That's what we will see. For an astronomer, a tiny dot like this is an image. And with this image, you get a lot of information. Because when you see the tiny dot moving, you will know the orbit. By looking at the color of the dot, like looking if the dot is red, blue, or orange, you will know if it's a Venus-like, Earth-like, or Mars-like. If you look as well at what we call the spectrum, so the color, but at different, we spread the color of the planet, we'll be able to see as well the composition of the planet, the surface of the planet, and also the atmosphere of the planet, and see if the planet is like, once again, Earth, as basically an ocean. So those projects are big, expensive. The ELT will cost probably $1 billion. But the result of this research is, I think, an important step in the advancement of science and our own civilization. I just would like to finish by this. The consequences of finding a planet like Earth could be enormous. If you find a planet like Earth, you will see aliens from somewhere, from another planet. And when I meant aliens, I meant maybe some different type of chemistry, different type of microbes, or bacteria. If you observe a planet around Alpha Centauri, you will see a planet like Earth, but significantly older, 7.5 billion years old. So we basically see the future of our own planet. What could happen to a terrestrial planet after staying 7 billion years around the star? If you observe a planet, a lot of planets, maybe we'll find something very interesting around them. Maybe we'll find a planet which have a civilization. It looks like science fiction, but if there is intelligent life elsewhere, maybe this intelligent life will be detectable on these exoplanets. So this is, for instance, a picture, an artistic view by an artist who imaging a civilization that has covered the entire planet with gigantic cities. And we will be able then to see maybe the light of the city. So those discoveries could happen in the next 10, 20 years, because we are building those gigantic, extremely large telescopes. Maybe in 10, 20 years, when we take a nap and you will look at the sky and we want to know what star is what, This app will tell you as well that there is a planet in orbit those stars, or this star, and around this planet, in one of those planets is an Earth-like exoplanet, a planet like Earth. So that's what astronomers are doing at the moment. They're basically building the map of the galaxy, of the close vicinity of our own star, but we are building the map that in the future will be used by the next generation to visit, maybe, to go there, or maybe to build instruments or spacecraft that will be one day capable of exploring those new worlds. And I'm gonna finish by just telling you that the key point of my talk is that when you look at the sky, you do not see stars, you see planetary systems. So when you look at those planetary systems, now you know that elsewhere over there is planets, a lot of them. And in our galaxy, we have quantified that there is 300 million planets that could be habitable. So I'm betting that in between those 300 million planets potentially habitable, one of them has life. And if he has life, maybe over there, looking at us, there is another extraterrestrial being wondering the same question, asking if he's alone. Voilà, that's all. Thank you very much.
That was wonderful. Thank you so much for that presentation. So fascinating to think that there's so much out there we have still yet to explore. And I wish we didn't have to wait 40 years for that huge telescope to make it up to space, because I want to know what's out there now. But just really amazing to hear about all the research that's taking place now to make way for what's coming next. So thank you for the beautiful presentation and beautiful images also. We do have a few questions that came in. So I was thinking we could jump into a few. And if anyone else has questions, feel free to post them in the chat. And we'd love to have Dr. Marchis answer those for you. The first question that came in is, what effect does scintillation over several hundred parsecs have upon receiving or transmitting signals from Earth?
Can you repeat the question? I was drinking and I missed the beginning.
What effect does scintillation over several hundred parsecs have upon receiving or transmitting signals from Earth?
Scintillation?
I might be saying that wrong. Scintillation or scintillation?
Yeah, I think it's scintillation.
Okay.
The scintillation is not coming from the planet, from the distance. It's coming from the atmosphere of the planet. So if you go to space, you will not see the stars scintillating, like twinkling. There will be the brightness will remain constant because of that. So maybe I misunderstand the question, but the scintillation is not related to the distance between the worlds. It's related to the presence of an atmosphere. When you basically drive on the road and it's very hot in the summer, if you look at the edge of the road, you will see this kind of blur. Well, the scintillation is exactly that, except that we are looking, we're not looking through the atmosphere above the road, we're looking at the atmosphere above us.
Great, thank you. And another question that came in said, did you say that you can detect the composition of a planet based on its orbit? If so, can you say more about that?
So based on the orbit, we don't detect the composition of the planets. Based on if I say that was wrong, it's based on the size, and knowing the mass, we can infer the composition of the planet. When we do transit, the transit techniques detects only the size of the planet and its orbit. If you do what we call radial velocity, which is the motion of the star due to the presence of the planet, we detect the mass of the planet. So if you combine both, mass and size, you get the density. And from the density, you can make some assumption about the composition of the planet. You can know if the planet is terrestrial or if the planet is a gas giant, for instance. A gas giant like Saturn has a density of 0.9, so less than water, and an Earth-like exoplanet has a density of typically 5 grams cc. So that's the density of the rock. So from this, you can infer what kind of planet you're observing.
Great. And will the James Webb Telescope contribute to exoplanet research?
So the James Webb Space Telescope is not been designed for that. Of course he will, but the instruments on board are not really made for this. They were envisioned before we knew that there was exoplanets, sadly. One of the instruments, I forgot the name again, has been kind of redesigned a few years before the finalization, so it can do some observation of exoplanets and detect maybe exoplanet like the gigantic gas giants, which are interesting by themselves. So JWST will be able to image those gas giants, but JWST will be also able to detect transits. And in this case, remember, we don't see the planet, we see the shadow of the planet. But because JWST works in the mid-infrared, it will be able to analyze the light during the transit, and from that, sniff, get an idea of the composition of the atmosphere of the planet. So with JWST, we may be able to kind of have confirmation if a planet is Neptune-like, or if it's an ocean world that I mentioned. Those kind of weird planets that theoretically seems to exist, but have not yet been seen. Maybe JWST will be able to see those planets.
Another question that came in was regarding tidal lock. And the question is, can planets in tidal lock have life? And they're referring to maybe TRAPPIST-1 being in tidal lock to their sun.
Yeah, that's something I didn't mention. TRAPPIST-1 planets are so close to their sun that they are basically probably locked, like Mercury is locked in a weird configuration with our sun. So in this case, one side of the planet is often exposed to the sun, while the other side is always in the darkness. So of course, there will be a huge difference in temperature between the illuminated side and the dark side. So that's a problem to solve if you want to have life. That's one of the reasons I did not mention that there is life on TRAPPIST-1b and then not 1c or d or e, and then not really habitable because of this problem. It's a problem that is theorists are still working on. There is some claim that you could have life just at the edge of these two areas, because the temperature will be exactly the appropriate one, but it will be a very narrow area of the planet.
That's fascinating. And we have one last question that came in, and this person's wondering if there's been any recent radio signals found by SETI.
I don't do radio signal, so I cannot really answer to that, but I don't think there was an increase of radio signal reported so far.
Well, thank you so much, Dr. Marchis. This was a wonderful, interesting talk and beautiful talk. I loved seeing all the images and just exciting to hear about the research that's happening and what's coming next. And thank you to the SETI Institute for this amazing talk. Thank you all for joining in. We really appreciate you all being with us this evening. And I just want to let you all know that we will be continuing this partnership with Chabot Space and Science Center and the SETI Institute into 2021. And we would love to see you all in January. And please consider donating to the SETI Institute and to Chabot Space and Science Center. We are both nonprofit institutions, and during this time, really appreciate any contributions. And thank you all for joining us, and we look forward to seeing you next time. Have a wonderful night, everyone.
Thank you very much, Jessica. Thank you very much.